Hello, welcome to this lesson of the Linear Algebra Tutor. In this section we're going to again continue with systems of equations and using matrices and row reductions to solve them. But here we're going to tackle our first system of equations that we call inconsistent. All right, so remember the couple of examples we've done so far, what we were trying to do was take our system of equations and create an augmented matrix and transform the left-hand side of that matrix into a diagonal matrix, and then we can read the solutions directly off. So if you were able to take that augmented matrix and manipulate it into being a diagonal matrix like that, then you are basically finished and you can read the solution right off of it. We call that a consistent system. When you have a set of linear equations like this and you can do that and read a unique solution off of the paper there or out of the matrix, then we say it's consistent. Here I'm going to show you a system that we call inconsistent, which means it doesn't have a solution. So let's get started and just write down our system of equations and just kind of go, and we'll pretend that we don't know what it's going to be, and we'll just see how the solution falls out. So x plus 3y is equal to 5. 2x minus y is equal to 3. Negative x plus 4y is equal to 9. So the first thing to notice is that we have two variables, x and y, but we have three equations. So at first you might wonder, well, why are we doing that? Why do we have more equations than we do variables? Well, when you think about it, each one of these equations is a line. When you have two variables like x and y and they're linear like that, then they're going to form a line. If I were to solve this equation for y, make it y equals something in terms of x, and solve this one for y in terms of x, and solve this one for y in terms of x, I would have three lines. Y is equal to mx plus b, basically, and I could plot those lines. So this set of equations is three lines. Now, if I end up getting a situation where when I plotted all three lines cross in a nice point right here, and this point is common to all three lines, then the xy value of this point is going to be what we're going to find the solution. It's going to be called the solution of the set of equations. But if, when I plot these guys, I get something like this, where I have two lines that cross up there, and the third one cuts across like that, then you see that each of the lines cross the other guy, but there's no common set of points in x and y that are common to all three equations. So if the lines end up looking like this, we'll have a consistent solution. If the lines look like this, then there will not be a single point in space where all of those lines coincide, so we won't have a solution. So I'm not going to beat around the bush. This set of equations is going to be inconsistent. Let's see how the math actually shows us that. So what we want to do is create an augmented matrix here. So let's go ahead and start by writing this down. We have a 1 here and a 3 here. We'll make our dotted line, and then we'll have a 5 on the other side. Here we have a 2. Here we have a negative 1. Here we have a 3. Here we have a negative 1, here we have a 4, and here we have a 9. So here's our augmented matrix. Now effectively what we're trying to do is manipulate it and get it diagonal, or as close to a diagonal as we can get, and then we'll just see how everything falls out in the solution. So on the upper left hand side we already have a 1 here, so we're already in pretty good shape there. We don't want to do anything there, so let's try to put zeros down here. So in order to do that, let me open the matrix out below it. Let's leave the first guy, the first line, intact. We won't mess with that. And on the second line, I'll multiply by negative 2. I'll multiply this line by negative 2, and I'll add it to here. So it would be negative 2 times row 1 plus row 2. When I do it here, I get a 0. Negative 2 times 3 is negative 6, plus this is negative 7. Negative 2 times this would be negative 10, plus this would be also negative 7. So that's what we get in the second row there. And I want to get a 0 here as well, so I'm going to just add the first row to the third row. So I'll just call it row 1 plus row 3. When I add this to this, I get a 0. When I add this to this, I get a 7. When I add this to this, I get a 14. So far everything is behaving itself just fine. And what I would like to do next is continue down below it, and I'll again leave the top alone. 1, 3, dash line with a 5, like this. Now we're trying to make a diagonal, or as close to a diagonal as we can, so we want a 1 right here. So the easiest way to do that is just to multiply this by negative 1/7 times row 2. Negative 1/7 times this is going to give me 0. Negative 1/7 times this will give me positive 1. Negative 1/7 times this will give me positive 1. All right? And ultimately, I want to try to get a 0 underneath this as well, but just for giggles, just to make it, mix up the variety a little bit, let me go ahead and multiply this guy by positive 1/7 times R3. That's going to give me 0. Positive 1/7 times this will give me 1. Positive 1/7 times this will give me 2. So far it seems to be pretty well behaved. Let us go down here and let me go ahead and continue the operations over here. Let me go ahead and continue the operations over here. So what I want to do next is I want to open up another matrix here, and I want to, on the top row, notice that once we have the ones like this, we want to put a 0 above. We want zeros everywhere else as far as we can get them. So let's put a 0 right there. So the way we do that is we multiply this row by -3, and we add it to this. So for this, let me scoot this over and give me a little more space so I have room to write. We'll multiply this row by -3, so it's -3 times row 2, and we'll add it to row 1. Now when we do that, we add -3 times this gives us 0. We add it to that, we retain the 1. -3 times this gives us -3, plus that gives us 0. -3 times this gives me -3, plus this is 2. So we'll close our matrix. The middle row we'll just leave alone, 0, 1, 1. And the last row, typically we want zeros underneath our diagonal elements as well, so let's make a 0 there. So the way I'm going to do that is I'm going to do -1 times this row, and I'll add it to this row. So it'll be negative row 2 plus row 3. Of course, row 2 has a 0 here, so when I add it here, I'm going to keep a 0. Negative of this times this plus this is going to give me a 0. -1 times this gives me -1. I add it to this, I also get a positive 1. So I've gotten this guy down to a situation where my final augmented matrix is about as reduced as I can. It's as close to a diagonalized matrix that I can get here. So I've got 1, 1, 0, 0, and it turns out that when I do all of this stuff, I get 0, 0 here as well. So you may not realize at first glance that this is an inconsistent system, so the way you need to figure that out is attempt to read the solution off of the board here. So since we have diagonal elements here, this is going to be, this column is for x and this column is for y. So we know that x, according to the solution, is equal to 2, y is equal to 1. But you cannot ignore, you might be tempted to stop here and say x is 2 and y is 1, right? But you would be wrong, because when you have the full matrix there and you've done all of the row operations, you have to look at every line in the matrix, and every line in the matrix is representing an equation. So if we ignore what the third line is telling us, we're effectively ignoring what the third equation is telling us. So when we take that into account, right, what this is saying, since there is a 0 here, is notice how this was 1 times y is equal to 1. This is telling us 0 times y is equal to 1. Let that sink in for a minute. This is telling us x is equal to 2. This is telling us y is equal to 1. This is telling us that 0 times y is equal to 1. Now I understand these two answers, but this answer is completely confusing. 0 times y is equal to 1. Tell me what value of y that could possibly be true for. Can I ever pick a value of y such that when I multiply it by 0, I get 1? There is no value of y that I could ever do that for. All right. If I pick y is equal to 1, if I pick y is equal to -5, if I pick y is equal to 10, if I pick y is equal to 1/2, doesn't matter. Whatever value of y I stick into this equation, if I multiply it by 0, I'm never, ever, ever going to get 1. There is no value of y that satisfies that. All right. So while you might be tempted to circle these first two answers and say, aha, here's our solution, you have to look at what everything is telling you. And what this is telling you is that no value of y satisfies this guy. So we say that for the whole system, there is no solution. All right, and we call this an inconsistent system. And this is effectively what you need to look for. Anytime, this particular example was chosen to be, a nice way to illustrate it without a ton of row reduction steps. But the same kind of idea applies to any type of system of equations you're trying to solve with matrices. When you get to the final place and you've reduced the thing down as far as you can, and you start reading the solutions off the lines, if you ever get 0 times one of your variables is equal to a non-zero value, then it doesn't satisfy it. All right, so what this is basically modeling is this situation right here. The 2 and the 1 is basically an intersection point between the first two equations. So the first two lines here do intersect at that point. But when you try to roll in the constraint of the third line, there is no way that it intersects with the other two guys. So there's no single point that you can pick in space in the xy plane that's going to satisfy the convergence of all three of those lines. So it's kind of easy to visualize crisscrossing lines in 2 dimensions. That's why I picked this problem. But the concept applies to 3 dimensions, 4 dimensions, however big your equations are. If you get 0 times a variable is equal to a non-zero value after you've reduced everything down, you've done everything right, then almost certainly you have an inconsistent system because there's no way to satisfy that part. So be on the lookout for that. This is the first example of an inconsistent system. All right, so far we have, in the last 2 examples, we have covered consistent systems where we get a nice diagonal matrix, we get numbers on the right, we can read the solutions off, so we have a nice identifiable solution point for those system of equations. Now we've identified that you can have inconsistent system where you can just tell by how the matrix, when you simplify the matrix, what comes out of it is basically impossible to satisfy. That tells us we have an inconsistent system. Now in the next lesson what we're going to do is learn about when we have a system of equations that can have an infinite number of solutions. So not just one solution or 2 solutions, but an infinity of solutions. So we'll talk about that in the next lesson.